So here we have a triangle whose side lengths are represented by the little a, b, and c, and the interior angles are represented by the big a, b, and c. I am going to verify the cosine rule, which states that for all such triangles, c squared is equal to a squared plus b squared minus 2ab cos c. Okay, so to start off, I'm going to draw a line from angle A to side A such that it is perpendicular to side A. This splits side A into two segments of lengths A1 and A2. Let's say that the length of this dotted line is m. Using Pythagoras' theorem on first this right-hand side triangle, we can say that m squared is equal to b squared minus a2 squared. And then using Pythagoras' theorem on the other triangle, we can say that m squared is equal to c squared minus a1 squared. Therefore, c squared minus a1 squared is equal to b squared minus a2 squared. And c squared is equal to b squared plus a1 squared minus a2 squared. Now, if we look at this right-hand triangle, we can see that a2 is the side adjacent to angle C, and B is the hypotenuse. Therefore, A2 is going to be equal to B cos C. And we can see from before that A1 plus A2 is equal to A. Therefore, A1 is going to be equal to A minus A2, which is A minus B cos C. Okay, so if we put these expressions for A1 and A2 into our formula from before, we get that C squared is equal to B squared plus A minus B cos C squared minus B cos C squared. And expanding these out, we get that C squared is equal to B squared plus A squared minus 2AB cos C plus B squared cos squared of C minus B squared cos squared of C. These two terms here will cancel out, which just leaves us with C squared is equal to A squared plus B squared minus 2AB cos C. So this is our cosine rule. If we consider the case of a right-angled triangle, then C is equal to 90 degrees, and we know that cos of 90 degrees is 0, therefore this term will disappear, and it just leaves us with C squared is equal to A squared plus B squared, which we know to be Pythagoras' theorem for right-angled triangles.